enantiomers can only be separated in a chiral environment, right? So remember that they have the same melting point, same boiling point, same intermolecular forces, same bond strength, same everything. And so the only way we can separate them is in a chiral environment. To go back to our hand and glove analogy, right? It would be very, very tricky for me to separate gloves without a hand to reference with that, or a brain that remembers what hands look like, right? So to build a machine to separate right and left gloves would be very tricky. Now, this doesn't apply to diastereomers. Diastereomers can be separated in an achiral environment. So for instance, here, these two molecules in black are enantiomers. They're mirror images of each other. And so it's very difficult. I cannot take one of them away in an achiral environment. I can't separate them. But you can kind of see how maybe this is a diastereomer of these two. I change one configuration, but not all of them. You can kind of see how maybe this one might have different intermolecular forces as these two, right? So all of them have the OHs maybe pointing in the same direction most of the time, but now this ether part of the molecule is sticking in a different direction, right? So it's very common for diastereomers to have different physical properties. And again, if we walk back even before we learned about chirality, cis and trans alkenes are diastereomers of each other, right? They are different shapes, but with the same atoms connected in the same order. So diastereomers can be separated in an achiral environment, can be boiling point difference, melting points, all the things that you will learn about in organic lab, hopefully. But enantiomers require a chiral environment. Another last piece of nomenclature. We consider all of these things, enantiomers and diastereomers both, stereoisomers. So stereoisomers is a catch-all term that basically says same atoms, same connectivity, different configurations. So all of these would be stereoisomers of each other. And we can even do a quick math to say how many stereoisomers are possible. And to do that, all we need to do is know how many stereocenters we have. If every stereocenter can be either R or S, then it stands to reason that we can just take 2 to the nth power, where n is that number of chiral centers, and that gives us the total number of stereoisomers. So for this compound, how many possible stereoisomers are there? Well, there's 3 stereocenters, and so in this case, there would be 8 possible stereoisomers. And that would exist as 4 pairs of enantiomers, right? So again, here's 2 of the stereoisomers. That's 1 enantiomeric pair, right? I've got this one that's kind of all coming out. I've got the all going in one. That's its enantiomer. So that's one way to calculate stereoisomers, which is a blanket term to encompass both enantiomers and diastereomers. So as I've said, lots of times drug makers want to make only one enantiomer and not the other one. And that is very difficult for us to do in the lab. Your body does it really well. Enzymes, they're all chiral. They do chiral organic synthesis amazingly. I am hella jealous of every single protein in my body. I have feelings toward it that are complex. One way to get a single enantiomer would be to start with a racemic mixture and go from there. So this first strategy to get one enantiomer free, we call derivatization. So trying to make it into something else. So let's say I start with a racemic mixture of 2 enantiomers, R and S, right? I can use organic synthesis to attach a chiral compound to both of them. And here, let's say I've got a single enantiomer compound. Where do I get that? Well, like I said, nature is actually really good at making single enantiomer compounds, right? Amino acids, there's lots of natural products around there. Menthol, I mentioned earlier. Lots of natural products are only found as one enantiomer. Table sugar is chiral, as you'll see in lab this week. So I can take a natural and maybe cheap chiral compound and attach it to both of my enantiomers. If I do that, then this mixture of what we'll call RR and RS, that's a diastereomeric mixture now. And as I said, I can separate diastereomers using the typical lab technique that I'm good at. I can separate them by melting point. I can separate them by boiling one away from the other. Usually what happens is that one of these is a lot more soluble in some solvent than the other. So I would dissolve them both up and then wait, and one of them would crystallize out of solution, but the other one wouldn't. Okay? And so I would separate them. I would take those crystals, let's say, that is pure this, and then I would just do more lab chemistry to take that piece off to get back to the original thing. Okay, so there are pros and cons to this approach. The pro is that it generally works. We can generally find chiral things like this pretty cheap that give us a good way to separate diastereomers, so it's pretty straightforward. There are a lot of cons though. One con is that the maximum yield from my racemic mixture is 50%. Right? So right off the bat, I am losing all of this S stuff. Just in terms of being, environmentally conscious, this is wasting a whole lot of material. The other problem is that I don't like to do lab chemistry if I can help it, because lots of times my yield for chemical reactions is not perfect. Right? And so in this thing, my maximum yield to get this out is 50%, but also it's not going to be 50% because this step isn't perfect and that step isn't perfect. And so there's lots of things that can go wrong here. So while this is a good strategy and it works, there are some downsides to it. I can also separate enantiomers physically in some chiral environment. So a common way to do this is what's called a column. So imagine I have some solid material, and hanging off that solid material is some chiral molecule. Right? Again, hopefully it's some chiral thing that's relatively cheap, some natural product. If I sort of flow some mixture of enantiomers past that solid support, one of these, R versus S, is going to stick to the R's on the column more than the other one. And once you get into lab, you'll get a sense of how we separate on columns quite a bit. But the idea here is that because one of these enantiomers is going to be stickier than the other, if I simply just kind of collect them at the bottom of this column, I'm going to get hopefully one and not the other. You can imagine that a really nice chiral environment is biological. So organisms are chiral, you are chiral. Sometimes we can use yeast to do this kind of thing. We can take advantage of organisms' ability to tell one enantiomer from another. So for instance, if chemists that have a compound that looks like this is a diester. It's a meso compound. So if in the lab, if I wanted to sort of chop these ends off to get to get one OH or to get the other, that's a tall order. I don't know any way that I can pick one off but not the other. But people can use enzyme from pig livers, pig liver esterase. You buy it as a dehydrated powder and you put it in your flask, and that actually allows you to chop one of those esters off but not the other. And there's actually a lot of synthesis like this where you buy some dehydrated enzyme and essentially hijack it to do the laboratory chemistry that you'd want to do, right? So now I have a essentially chirally pure product that I can go make my single enantiomer drug from. And I can go make my single enantiomer drug now from this enantiomerically pure product. So this is a really cool thing. And it's also a really active area of research. I know that Professor Allison Narayan at the University of Michigan is a leader in this, just trying to see what other chemistry we can do, taking advantage of the enzymes that nature has already made for us. I know I said there's not going to be any math in this course. There's a little bit of math that we'll go through here. It's not tough, I promise. One question we might have is, how do I know how enantiomerically pure my sample is? Right, so let's say that I'm in a lab. I mentioned before that making single enantiomeric compounds is tough, and it's not a perfect thing. So I know that pure minus menthol has an optical rotation of negative 50 degrees, and that positive menthol has a, being its enantiomer, has an equal and opposite rotation. So let's say that I make some menthol and I get a negative 20 value. I know that all I have is the two enantiomers in there, but I don't know the ratio of the enantiomers. So how do I find that from its rotation? Here's one way to think about it. If I have 100% of pure minus menthol, then the rotation would be minus 50 degrees. If I have minus 20 degrees, minus 20 is 40% of 50. So that means that only 40% of my sample is minus. The rest of it is racemic, right? Remember, racemic mixture doesn't rotate light at all. But we can unpack that a little bit, right? Because what does 60% racemic mean? 60% racemic means 30% plus and 30% minus within that, right? It's just that for every plus molecule is counteracted, I guess, by a minus molecule. And so if I'm looking at how much is all minus, I have to take this minus from the racemic and add it to the excess minus that gives the sample its optical rotation. So overall, this is 30% plus and 70% minus. So one way to think about this is in terms of enantiomeric excess, or percent EE. In its simplest form, that's simply the percent of the major minus the percent of the minor enantiomer. So here I've got 70% minus, I've got 30% plus. So 70 minus 30 is 40. So the percent enantiomeric of this mixture would be 40% enantiomeric excess. But I could also get that number just by dividing my rotation, my observed rotation, dividing that by the pure enantiomer. So for instance, if I observe negative 20 degrees and I know that pure menthol should be 50 degrees, that also gives me 40%. So for a racemic mixture, my rotation is 0 and my enantiomeric excess is 0. For a pure compound, my enantiomeric excess is going to be 100%, and my rotation will be just that given number. So I can use this math to go both ways. If I'm given the experimental rotation, I can find my percent of plus and minus, and I think kind of drawing it out like this and thinking about that is helpful. Or if I'm given the percentages, I can go back and calculate what I expect the rotation to be. And the linking there is this enantiomeric excess.